Hello everyone, and thank you for joining us for today's Surface Measurement Systems live webinar and Q&A. Today we'll be discussing the topic of analysis of wood and building materials using dynamic vapor sorption, and we're very lucky to have with us today our DVS product manager, Dr. Damiano Cattaneo. Dr. Cattaneo is our senior instrumentation scientist for surface measurement systems and obtained his PhD in chemistry, material sciences, from the University of St Andrews, UK in December 2015. His research project was focused on using porous materials for biomedical applications. Specifically, he investigated the development of porous coordination polymers, such as MOFs, COFs, and porous organic cages, and zeolites as gas and drug delivery systems for biomedical devices. Dr. Cattaneo has a master's degree in medicinal chemistry from the Università degli Studi di Milano in Italy. And during the last year of his master's, he also worked as a researcher on drug discovery and total synthesis of anti-Parkinson's drugs at the Department of Pharmaceutical Sciences at Prieto Pretesi in Milan, Italy. Before we continue with today's presentation, I just wanted to remind everyone there is a live Q&A at the end of the session, and there are two ways you can take part. Way one is that you can submit your questions in writing in the questions tab of the control panel, and I will submit that question to Dr. Cattaneo at the end of the presentation. Or alternatively, if you would like to ask the question yourself and have the opportunity to unmute your microphone and direct the question to Damiano, please simply raise your hand and I will let you know when you can unmute your microphone to ask your question. So once again, questions can be submitted throughout the presentation in the questions tab in writing, or you can raise your hand at the end and I will let you know when you can unmute your microphone. So without further ado, I will hand over to Dr. Damiano Cattaneo to begin his presentation.
Thank you very much, John. I hope you can see my screen, and I'm gonna start my presentation here. As mentioned by John, today I would like to talk a little bit about analysis of wood using building material using gravimetric technique called DVS. The presentation of today will cover a little bit of introduction about the technique, and then we are going to be focusing specifically on a few applications and a few examples of application of DVS for these specific materials. So why do we actually are interested in using gravimetric technique to analyze this type of material? Well, in general, what we are looking at mainly with DVS is absorption of water or humidity. And humidity usually affects the performance of building and wood material, the storage, the processing, and the formulation of this material. Usually, in fact, these materials are exposed to a variety of temperature and relative humidity that could cause variation of dimension or porosity or structure of the material, which then affect the mechanical property of the material, but also the fragility or the stress resistance of this type of material. For this specific reason, we are interested in to analyze this property throughout a gravimetric technique. We know that moisture plays, in fact, a crucial role in the structure of the material, but also in the long-term stability of the material itself. We are going to analyze different types of material, specifically from wood to straw material in different particle size. And we're going to see how these can affect the property and the absorption capability of this material. We know, for example, that oriented strand, which are more unstable when exposed to a high level of humidity, can lead to mechanical stress and also changing the color of the material, changing the aesthetic of the material. One of the other parameters that we're going to have a look at is hysteresis, which is the gap between the absorption and desorption. So when we pour water on top of a sample or vapor on top of a sample, it will uptake with a certain type of profile. And when we try to dry the sample, the profile will be different. The gap between the absorption and desorption profile, the hysteresis, will be representing how much water stays trapped and how much energy is required to remove that water. Some material have narrower gap of hysteresis, some material has smaller gap of hysteresis, and that can cause a fluctuation in the water content of the material at each temperature and the total stability of the material itself. So different type of material obviously are affected in different ways, but even the same type of material, changing the species, changing the grain direction, changing the age or the location where this material is provided, for example, for wood material, can affect the property, the water content, and the water absorption of this type of material. So what we're going to talk about today is how do we use DVS to characterize these parameters. We're going to look at the general concept of DVS, how do we run an experiment with DVS, and then how can we use the data collected on this type of sample to extrapolate information in regard to the material itself. So DVS is an analytical technique that allows you to collect information about the sample. Now, we have a variety of methods that can give us information about our sample. Different technique provides different way to collect data. So we have methods that use energy to transfer energy through a sample and use that to collect data. For example, spectroscopy or X-ray are usually information that use energy transfer on the sample to collect information. Calorimetry or thermodynamics, TGA, for example, will use energy. DVS, on the other hand, use molecules, so use matter to collect information into regard to the sample itself. So in more detail, if you think about XRD or powder XRD or NMR or FTIR, we provide energy. The energy is absorbed and transferred through the sample and then is released. And we usually have a detector that measures these release of energy. Optical measurement or SEM or particle size measurement are usually based on this type of information. From a point of view of heat, we have DSC of TGA. We provide heat to the sample. The sample reacts to the presence of heat, decompose or dries. We record the change by a reaction with the sample while providing energy. In DVS is very similar. The concept is just a different source of information. So here we have our sample. We start usually from a dry condition of the sample, and then we introduce molecule or vapor, for example, water. And water molecule will absorb on the sample itself. So we call it adsorption if it's only on the top layer of the sample. If the molecule penetrates through the bulk of the sample, we usually refer to it as absorption. This process can be reversible or irreversible. And when we reduce the molecule around the sample, we technically dry the sample. And if the sample has not a strong bonding interaction with the molecule that we introduce, we see a mass loss. We see a reduction of the mass of the sample. So more specifically, we are going to talk about two phenomena, which are absorption and adsorption. Adsorption is usually related to two phenomena, which are phase absorption and chemisorption. And absorption is obviously through the bulk of the material. So bulk absorption or absorption into the lattice structure is usually what relates to that part of the absorption process. So the method that we are usually using is based actually on an older procedure. So you might be familiar, because it's reported in Pharmacopoeia, or is also used in older technique, to a jar method. A jar method will be very simply, we have a series of desiccators that contain saturated solution of salt at the bottom of the desiccator. This creates a constant level of humidity inside the desiccator. We dry our sample, we record an initial mass of the sample, and then we load the sample into the desiccator. In the desiccator, they will be exposed to a constant value of humidity over time. We wait for a few days, we remove the sample from the desiccator, we record the mass, we put it back in, and repeat the process. Each desiccator has a different saturated solution, which has a different level of humidity. So we have, for example, lithium chloride will have 11%, sodium chloride would have 75%, potassium nitrate will have 89%. And that will represent a point on your absorption. Once every single sample has reached equilibrium in each desiccator, then you can use the mass recorded or the delta mass recorded to build up an isotherm. The same concept is performed in a DVS. However, it's a continuous experiment, it's a dynamic experiment. So what we're using is a carrier gas to push a constant value of molecule on top of the sample, and we measure the mass change by using a microbalance, by constantly recording the mass change over time. So the difference between the two techniques is mainly based on the first amount of sample required to perform the experiment. A jar method will require grams of sample. It's a labor work in which you have to move the sample in and out. So a bigger amount of sample will allow you to collect more accurate data because you will reduce the error in the measurement. In dynamic vapor sorption, we use a microbalance. Consequently, we can load smaller amount of sample, and that allows us to obtain similar type of repeatability compared to a jar method without actually interfering with the measurement, but also allows us to use very, very tiny amount of sample. The process on the left side, so on the jar method, is usually static condition. There is no force that drives the reaching of the equilibrium between the ambient around the sample and the sample itself. It's just diffusion. While in a dynamic vapor sorption, we have a carrier gas, usually 200 milliliter per minute of nitrogen or air, that we use to push molecule on top of the surface of the sample. And that is what allows us to reach equilibrium. So because it's dynamic, it will have a faster condition of equilibrium. The time required for the experiment is significantly different because on one side we have a big sample and a static mode, and on the other side we have a small sample and a dynamic mode. The difference can be very significant, and I will show you in a second how much can be the difference between these two conditions. Lastly, there is cross-contamination. Every time we remove the sample from the jar to record the mass, we expose it to a different level of temperature in the lab, different level of humidity, the lab itself, which can cause cross-contamination first and error in the reading. In a dynamic vapor sorption, we load the sample and we never touch the sample again. So the entire experiment is recorded without actually interfering with the measurement. We can measure full cycle of absorption, desorption without interfering at all. So no cross-contamination, but also faster experiment. Here you can see from left to right a side-to-side kinetic data plot of an experiment performed on the left side with a jar method and on the right side with a dynamic vapor sorption. The left side shows only absorption, so only increase in the humidity, 300 days. On the right side, we have the dynamic vapor sorption experiment of absorption and desorption, about 4.2 days for the full set of data. Now, if we record the data and we plot them as isotherm, which is the plot of relative humidity over percentage mass change, you will see that the jar method only offers data from the absorption kinetic, while the dynamic vapor sorption will give us data from absorption and desorption, as well as the gap of hysteresis, which is the difference between these two lines, which we talked about before, and we're going to analyze them in a second. So how does the DVS actually work? How does it perform the experiment? So this is a general schematic of any real DVS that we use in our labs. We have a carrier gas that is pushed through mass flow controller, through valve. One side will be considered dry, which is the carrier gas that we use to dry the sample. And one other side is connected to a bottle of water, the headspace of a bottle of water, and that will represent wet. The two gas will mix, will push in front of a sensor that will read the humidity as a reference value, and then it will go to a sample and a reference chamber, which are connected to a microbalance. The microbalance that you see represented here is basically an old pharmacist balance with two plates. One side is sample and one side is reference. What is the difference between sample and reference? They are perfectly identical. The system is perfectly symmetrical. And the reason why they are identical is because we are trying to achieve symmetry to get better absorption data. What I mean by that is what we are doing is we are pushing molecule of water into a chamber where we have our sample. Now, the molecule of water will absorb everywhere. We cannot control where molecule of water goes. So they will absorb on the sample, but they will also absorb on the pan, on the end wire, on the side of the chamber. So what we want to measure is only the mass change related to the sample itself. Now, the best way to do it is to just make it symmetrical. So if everything is on the sample side is identical on the reference side, and the only difference is the sample itself, when we push molecule in the chamber, the part that we only measure is the delta, which is the sample itself. So that's basically the schematic I represent you how we collect data from a gravimetric perspective. So if we have to run a simple experiment, usually we put a sample into the chamber. We will use a carrier gas to dry the sample progressively. And then after the sample is dried, we will progressively increase the partial pressure and wait for the sample to reach equilibrium. Usually we do it in step. We go 0, 10, 20, 30% partial pressure, and we use the data collected from the balance itself to record the mass reading. Once the sample reaches equilibrium at each stage, the software automatically moves to the next stage. So the mass of the sample will usually increase progressively until it reaches equilibrium, and then we can move to the next stage. So we can go 0, for example, to 90%, and then we can repeat the same process in inverse and do the desorption stages, going from 90 back to 0. Once we collect all this set of data of absorption and desorption, we can use the data to build up our kinetic. And if we can take each point of equilibrium at the end of each stage of the absorption and the desorption, and we plot it against the relative humidity, then we can get our isotemp plot. So that's basically how we run an experiment. So what would the data look like? So here we have a sample, for example, of wood material. And we are doing, so here we have 600 milligrams of wood. And here we are doing a kinetic data, an isotemp plot of our wood sample. We are going at 0 to 90, 10% step. And we have the cycle of absorption, which is the red line, and the desorption on the blue line. So these represent the final result of our experimental data. I'm going to use this data to actually highlight something interesting about how particle size will affect and processing of the sample will affect the total water content of a sample. So this is a chunk of wood that we're just measuring at 25 degrees C. If we look at the percentage mass change, so the amount of mass of water that goes into the sample, let's say 85% or 90%, which is the highest step that we've done in this experiment, we can see that it goes over 10%. Approximately 11% partial percentage mass change. If we take the same sample, but in this case we ground it, so in sawdust, and we only put 10 milligrams of this sample, we can see that the isotemp plot is different. The gap of hysteresis is bigger, but also the percentage mass change is significantly higher. You can see that now it's almost 20% mass change, the amount of water that the same sample can absorb. So this is just give you an idea of how different particle size, but also different processes can affect the amount of water that the sample can absorb. We affected total surface area, water solution capacity, and hysteresis shape, just by grinding the same sample to a different particle size. So obviously, which straw that we are talking about have been used for different type of application as bioabsorbent, as wastewater treatment, or composite material, or biofluid. Part of the process part of the treatment that is applied to this material can specifically affect the amount of water that the sample is able to absorb. And we can also study how these processes are actually affecting the absorption property of the material itself. What we are doing actually is changing not only the surface chemistry of the material, so the accessibility of chemicals to the surface of the material, but the total surface area of the material, the hydrophobicity of hydrophilicity. We are removing waxes from one side, and on the other side, we might be able to also increase the amorphous content of the material. And usually the amorphous version of the material tend to have a higher solubility compared to the crystalline form of the material itself. So those parameters that we are affecting are actually then affecting the total water sorption capacity of the sample itself. Now, one of the things that we can use, one of the things that we can analyze using DBS is measuring the specific capability of absorb water, but also the total surface area of the material itself. Now, we have different solvents that we can use to measure BT surface area. The choice of solvent really depends on the relationship between the solvent and the material that we want to analyze. And what I mean by that is I cannot pre-pick a solvent that I'm going to use for my experiment. Some material will have specific solution capacity that will allow to use water, for example, to measure BT surface area. However, other material will be too hydrophobic to actually be able to use water for the experiment, so we might have to move to organic solvent. But just to give you an idea of what we are talking about, here is an example of kinetic data on straw material. We are measuring absorption and desorption. So here is the kinetic data plot. So in red line, you can see the percentage mass change over time. And in blue line, you can see the target partial pressure that we are increasing and decreasing. Here is a full isotherm plot, about 4 days of experiment. And you can see here the material have a very significant percentage mass change, but it also tells us the material more or less reach equilibrium in each stage, which is what we are looking for, a plateau condition of the mass at each stage of equilibrium. Now, if we take this data, each point of equilibrium, and we plot it against the percentage mass change, what we can see here is our isotherm plot. We a small gap of hysteresis between the absorption and desorption, which is usually indicating the fact that there is a certain amount of energy involved in the desorption of water from this sample compared to the absorption. So if you think about this set of data specifically, if you look at, for example, this step at 50%, the absorption cycle, which is the red line, and the desorption cycle, which is the blue line, you can see that the absorption cycle at 50%, the mass of the sample is much higher during desorption than in the absorption. If you have to translate it from a value of energy, it means that the water prefer to stay inside the sample rather than outside the sample while the sample is wet, which means that I have to go to a lower level of humidity, let's say 40 or 30%, to get the same level of mass that I will get during the absorption cycle, just because the material has a high affinity for water. So if I look at the isotherm plot, what I can see here is that this section between, let's say, 5 to 35% partial pressure, which is this area right here, as a linear configuration. You can see that it's basically flat. It curves up towards the end, but at the initial section of my isotherm plot is perfectly linear. Usually we define this type of isotherm as a type 2 isotherm, which usually can be integrated to calculate surface area. The way we calculate surface area is exactly the same process that a nitrogen solution experiment will use to measure surface area, which is basically apply the Bram-Yuan-Teller equation. So what's the crux of the process of measuring surface area? The first parameter that we have to measure surface area is a linear isotherm plot in the section between 5 and 35% partial pressure. So if I show you any potential kinetic type of absorption, so independently of what solvent you're using and what sample you're using, the type of isotherm that you're going to get is one of these 6. There are small variation, but it's one of these 6. Now, if you look at this isotherm plot, which are commonly reported in the literature, the only 2 plots that have a linear section in the lower region, which is called the monolayer region, are type 2 and type 4, because they have this linear section right here. Anything that is non-linear which is more curved, usually does not describe a monolayer formation and does not allow to use for a calculation of DET surface area. So why are we obsessed with this linearity? The reason why we are obsessed with the linearity is because the way we calculate surface area is by measuring, actually by calculating, how much is the volume of the monolayer of molecule that absorb on the surface of our sample. So if we know the volume of the monolayer of the molecule absorbed on our sample, we know the mass of the sample because we measure it at the beginning of the experiment, and we know the cross-section area of the molecule because we know we are pushing water on top of the sample. So we know the cross-section area of water. By knowing these two parameters and by knowing the volume of the monolayer, we can automatically calculate the surface area of the sample divided by the mass of the sample is the specific surface area. So why linearity? Here you can see the equation of the BT, Brown-Teller equation. And if you can see the way this equation is presented is the equation of a line. It tells you that y equal mx plus q. So as long as the plot is linear, we can fit a line in the section of the monolayer between 5 and 30% partial pressure. We can automatically find the stiffness, these parameter, the stiffness of the line, and then we can find the intercept, which is this parameter. By knowing these two parameters, we automatically know the volume of the monolayer because every other factor is pre-known during the experiment. So what we are doing here is taking this our plot and fitting a line literally between 5 and 35% partial pressure. So when we take our isotherm data from kinetic point of view, what we are doing is fitting a line in between the point and trying to get the best R-squared value, so the best fit possible. Automatically, we will get a value of monolayer and a specific surface area calculation. So that's basically what we are looking for. And the shape of the isotherm depends on the interaction between the solvent that we are picking for the experiment and the sample itself. So what solvent to pick? Think about the property of the material that we are using and the way those molecules will absorb on the surface of the material. So if the delta H of absorption between these molecule and the surface of the sample is high enough, then the molecule will spread on the surface as a monolayer. But if the delta H of condensation of the solvent is higher than the delta H of absorption, then consequentially molecule will form droplet rather than spreading uniformly. So if you think about a piece of wood untreated, then usually that type of material, if it doesn't have too much wax on top of it, will tend to absorb as much water as possible, forming a monolayer. And that will allow you to measure surface area. However, if that material is being treated or coated with specific polymer, the polymer surface usually has a lower level of hydrophilicity. Consequentially, it will form droplet rather than spreading uniformly. So consequentially, it won't allow you to use water on the surface of the sample, but it will require a different solvent. So technically, it's based on surface contact. It's based on surface interaction and energy of equilibrium. You can see basically this example. You want a uniform coating, not droplet formation. So another couple of examples of application that we can do with DVS, and staying with water absorption for now, for the main application, we can have a comparison between same material, different treatment. So we have wheat straw here, and we're going to compare raw material and then material that being extruded at 100 RPM at 50 degrees Celsius, and that's being treated with 4% sodium hydroxide. After that, we're going to compare it with the same type of data, but we're going to look at after an extra additional washing as pre-treatment. So the data that you see over here, and I'm going to focus specifically on the difference between the raw material, which is sitting in the low hand here, and the material that has been extruded but washed only once, not twice. So the one that has 0.9 but not 0.9W. So you can see here that the 0,9 material has significantly higher uptake, but the gap of hysteresis is completely closed. You can see here there is a nice gap of hysteresis in the raw material, but it's gone completely when we do the extrusion. So as you can see here, basically the pre-treated sample has a significantly, almost double uptake of water, especially the high end of concentration. Probably because the washing has removed a lot of the amorphous region of the material, but and that removed part of the solubility. The sample does not show gap of hysteresis because there is less swelling of the pores, so less capillary condensation. Usually capillary condensation causes gap of hysteresis in the measurement that we are recording. Now, if we compare the last set of data, so the W sample compared to the treated sample, you can see here the treated sample have a significantly higher uptake, but it reverts back if we have a double washing. Now, this is telling us basically that we are able to revert back to the initial condition of the material, because basically it's very similar to the raw material that we started from. So the W, the version that has been washed, the total uptake is almost comparable. You can see here we are in the 0.2, 0.3 difference percentage mass change. So the, let's say, lower uptake of the pretreated material is likely to be due to the fact that we remove the amorphous material when we wash it, which is present after the extrusion, but remove after an extra washing. So the similarity between the raw material and the wash material indicates that when we modify our material, we are increasing the total solution capacity, but that is mainly related to the amorphous that we generate during the treatment. If we wash the sample after the treatment, the majority of the amorphous material which is modified, which is causing the higher uptake, is removed completely. Consequently, we go back basically to the initial property of the raw material. Before I conclude, I'm going to show you a couple of extra applications related to other type of study that we can do on DVS. Most of the studies that I show you so far are related to pure absorption and desorption and BET's measurement. I would like to show you something about diffusion and permeability, and a little bit of study also on cement material that we have done on DVS. Here is an example on film material. So this is an experiment on diffusion, and what we are measuring here is the diffusion capacity of the sample. So we have a polymer membrane, can be used as an insulation. In this case, we have isolated one side of the membrane. And what we are doing here is we want to measure the diffusion coefficient of this material at a specific temperature, let's say in presence of water. So the experiment itself is extremely simple. We dry our sample and we introduce a constant level of relative humidity, let's say 20 or 40 or 60%, you can see over here. And what we measure is the uptake, the mass uptake, which is the red line, over time. And we want to see how quickly it reaches equilibrium and what's the mass uptake at the equilibrium condition. Why? Because the diffusion and permeability parameter depends massively onto the absorption property of the sample itself. So what we are measuring here is flux of molecule of water through the membrane. We know the surface of the membrane, we can measure it, and we know the thickness of the membrane. We can measure that with a caliper. So what we can do here is measure the diffusion by measuring the mass uptake at the beginning of the experiment, MT, which is the fitting of this line, and then the mass at equilibrium condition, which is M infinite, which is the end of our curve. We then know the thickness of the membrane, we can measure it with a caliper, and automatically we already fill in the value of this equation. Consequently, we can calculate the diffusion coefficient per membrane at each stage of our experiment. Obviously, sometimes it can be difficult to isolate sites of membrane, specifically because, you know, water tends to absorb wherever it can. So one of the accessories that we usually use on DVS experiment is diffusion cell. These cells are made of metal and they have two O-rings in which we can clamp the membrane in it. we usually put a desiccant at the bottom of the membrane, and we measure the absorption capacity and the diffusion by basically exposing the membrane to water over time. We know the thickness of the membrane, we can measure at the beginning of the experiment, we know the area of the cell that is exposed on the outside, and we can measure the uptake over time. One of the questions that you might ask is, why do we have to add a desiccant on the bottom of the cell? So whenever we do this type of experiment, we only want to measure the uptake, the mass uptake, dependent on the diffusion, nothing related to a delta in humidity. What I mean by that is, let's picture that we prepare this cell in a very dry condition. So the inside of the cell is completely zero humidity. We put the membrane in, and then we load it into our DVS. We have no desiccant in it. We bump up the humidity to 20%. The humidity will penetrate through the membrane and absorb into the empty cell. So the delta at the beginning of the experiment will be 20 on the outside and 0 on the inside. But over time, the humidity will penetrate in the inside. So at some point, we're going to increase the humidity to an equilibrium condition, and that will lower the speed of the diffusion, because now we have 20 on the outside and 20 on the inside. The desiccant inside maintains a low level of humidity inside the cell, guarantee that we have a constant delta, so a constant diffusion value. The last experiment that I want to show you is a study on, this is actually an historical study that we perform on DVS using a kinetic measurement to describe the aging of mortar, wood, and brick material, something that we talked about at the beginning. How does the aging of the material affect the way they respond to presence of water? So this is doing an historical restoration of a building, and how replacing brick from old to new could affect the stability of the building or the integrity of the building itself. We take a few samples of different age of the same material. We expose it at 25 degrees C to 0 to 95% relative humidity, and we have a look at the way this material absorb water. So here is the data plotted. It's a lot of data. I'm not going to focus specifically on every single line of the data. However, what I wanted to show you here is, for example, the difference between older bricks, so older material, and newer material. The older material usually have a higher uptake of water in the higher end of our curve, compared to newer material, who tends to actually absorb less water but also be more reversible. If we plot the kinetic data, you can see here that from older to newer, our isotherm plot squish towards a lower level of uptake compared to the older material that usually tend to have more water in it and maintain more water inside the structure. Now, why is it important? Presence of water obviously is related to fungi and microbial growth, but also instability and disgregation of the material, or less prone to stress compared to the newer material, which offer a higher rigidity, also lower water content, so lower growth of fungi or mold. So that is exactly what I wanted to show you today, a few examples of application related to the use of DVS for this type of material. A few examples that I show you today indicates how we can study the way treatment, pre-treatment, or washing can affect the stability, but also the absorption capacity of the material, and how, for example, increasing the processing of a material can increase the amorphous content, consequentially increasing the sorption capacity of the material. A wash can also remove the new created amorphous material, consequentially reducing the total sorption capacity back potentially to the initial condition. Obviously, the study here is an ideal concept of how we can utilize DVS for this type of characterization. I've shown you mainly water uptake, specifically because this can be really related to the material stability and inert material adhesion and exterior weathering and fungi and mold growth. So this is exactly what I wanted to show you today. So I would like you to thank you all for your attention, and I will be happy to take any further question or any information that you want to have about our instrumentation.
Thank you, Damiano. It's a great presentation, and we've got a few questions in already, but before I ask that, I'll just remind our listeners, you can submit questions in writing in the questions tab, or you can raise your hand and I can let you unmute your microphone to ask the question directly. So first up, the first question we have is how much of the wood sample is typically used for DVS measurements? Can I measure a large block of wood of around 2 grams?
Sure. So the amount of sample required for the experiment really depends on a couple of parameters. In general, the instrumentation that we use can be equipped with 2 different variants of balances. We can have a low mass balance or we can have a high mass balance. A low mass balance usually can lift up to 1 gram of sample, and a high mass balance can go to 5 grams of sample. Now, do we need to run that amount of sample for this type of experiment? Well, that depends. Usually, a higher amount of sample is required for material that have low uptake of water. We measure mass change as a percentage, so we are not interested in absolute mass, we are interested only as a percentage mass change. So for material like wood material, which the material has a very, very high uptake of water, usually we don't need more than 100 milligrams of sample. Material that have a very low uptake, so less than 1% or even lower, we can go to higher mass of sample. Now, there is a question related to homogeneity. Sample can be potentially heterogeneous. Consequently, you want to have a sample that is significant for the type of study that you're doing. Increasing the mass of sample causes 2 things. It causes the fact that the experiment lasts longer because you need to reach equilibrium at each stage with a higher mass of sample. And sometimes it becomes difficult actually to be able to load that amount of sample as a volume, not as a mass, because it's a bigger sample physically. Consequently, what we actually recommend is, rather than trying to run a very, very big sample, is maybe more useful, and it actually saves time in the long run, to run in a couple of sample, 2 or 3 sample, which are smaller side, but they come from different spots of your, let's say, average sample. And that will allow you to run smaller mass, which means that the experiment is shorter, but also give it more significant, a 3-point variation that will, in the end, take the same amount of time as a big sample.
Well, thank you. A question here from Celine Pellerin. And firstly, she thanks you for an interesting presentation. And she asks, when doing a sorption and desorption cycle experiment, what is good practice regarding the relative humidity level when doing the 0 and for sample insertion? Should it be at 95% to avoid static buildup, or close to 0 to keep the sample dry?
Just to clarify, is this during drying? So is this during loading and unloading, or is this during the experimental data itself? Just to
I think this is during the loading. I think. From the question.
So in general, well, static can be a problem, but usually not on the unloading. We can use static gun before you load the sample to actually move the sample inside the chamber. Also, the sample usually sitting in your lab, so it's pre-wetted, because at least we live in UK, so there is a lot of humidity sitting in the lab that allows us to measure at least 15 to 50% relative humidity. So they kind of have a lot of water already into the sample. A little bit of use of the static gun can get rid of most of them. The buildup of static can happen during the experiment itself into the drying stage. That one, unfortunately, is a little bit unavoidable. And there is nothing to do with the way you load the sample. It's just related to the fact that we are filtering a lot of dry nitrogen or dry air to the sample, and we are reducing the humidity progressively. Having a bump up of humidity before you start the loading can pre-wet the chamber, but if the sample is significantly prone to static, at some point the static will build up and discharge. Unfortunately, that's nothing related to the measurement itself, is more related to the behavior of the sample in presence of the gas, dry gas.
Thank you. Tracy Zhang has asked, how do I know if the DVS is low balance or high balance?
Sure. So if you already own a DVS, usually the name of the instrument tells you more or less what balance you have. A low mass balance is usually called DVS1. A high mass balance is called DVS2. If you have any documentation related to the qualification protocol or the installation or anything related to the instrument, it will have a serial number. You can contact us with a serial number and we can tell you what balance is installed into your instrumentation. The easiest way to spot it is our instrument is shipped with a calibration weight. And the calibration weights are different because we require different masses for the two balances. So the calibration weight for a low mass balance is 100 milligram. The calibration weight for a high mass balance is 1 gram. So if you look at the calibration weight, it will tell you how much is the weight of the calibration weight. If it says it's 100 milligram, it's your low mass balance. It's 1 gram, it's a high mass balance.
Brilliant, thank you. We have a raised hand from Saeed Moghadem. So Saeed, if you would like to unmute your microphone, I will unmute you on my end as well.
Hi, thank you for an interesting talk. In your experiment, when you tested a membrane, isn't that the significant distance that you have between the absorbent and the membrane, also the space that you have on top of it will dominate the diffusion resistance rather than the membrane?
Sorry, can you repeat your question? So you're interested in the diffusion experiment, this experiment, right?
Yeah, in the case of membrane, you have a very significant this spacing between the material in the chamber and the membrane. That basically distance will dominate the diffusion resistance rather than the membrane. Isn't that true?
So the chamber itself, you mean the sample chamber, or do you mean in related to the diffusion cell?
Yeah, the diffusion cell.
Right. The part that is actually that we're actually measuring has no metal in it. There is a hole. So technically the water can just go through it right here. So we are exposing membrane directly to the gas line. We are not hiding it behind a block of metal. So that part is removed from the test itself. The parameter that we are using basically is the ability for the membrane to absorb from point of view of surface, but then to absorb through the bulk of the material directly in contact with the gas line, so directly in contact with the humidity. So when we use this type of accessory, or when you mount the membrane directly into the pan, directly into the chamber, or you load it into the pan, the exposure is direct. There is no delay in the exposure between molecule getting to the sample and molecule actually absorbing. The main factor that we also use is you can think that there is a delay in the generation between the point of where, for example, we send a command to the system to release a certain amount of molecule of water and the moment where the sample is actually starting to absorb. Technically, there is that delay. However, what we usually recommend for this type of experiment is physically inspecting the data of the mass uptake. So it doesn't matter when the system starts to generate, it only matters when the mass start to respond. So if you look at this set of data right here, we are not picking the set of data of the initial exposure or the initial coverage. We are looking for a constant uptake of a fitting that is basically a line, because that's the real point in which the diffusion is happening. Usually you have monolayer formation and absorption, then bulk absorption, and that's the part that we are actually looking at when we do the actual calculation. So in general, even if there is a small delay, we are not looking specifically at that delay. We're mainly looking at the part that is related to how the mass reading respond to the molecule absorption.
Thank you.
No problem.
Thank you, Saeed, and thank you, Damiano. A question here from Lei Han, and they ask, Since the measurement is very sensitive, how do you exclude the influence from factors like early wood, late wood, cutting and planning quality of the sample surface, sample thickness difference? They specify, how do you prepare the wood samples for DVS test? Is there a normal method or standard that we should follow?
Okay, so in general, the way we look at this type of experiment, or the comparison between experiment in which the material are, let's say, similar in type of structure, what we want to maintain is a uniformity in the way we analyze it. So what I mean by that is, if you're analyzing different type of wood, or wood from a different, same type of wood but different source or different age, usually you can cut it to more or less the same size. Now, material like wood have a very high uptake and a very high social exposure, so consequentially they don't have particular problem of getting water into the bulk of the material. They will absorb no matter what, but we prefer to have similar size of sample and similar dimension. So if you're looking at the a chunk of wood, usually, let's say you're running 50, 100 milligram of sample, and it's a tiny square of 0.5 centimeter by 0.5 centimeter. We usually recommend to maintain that type of measurement. We have systems that run parallel experiments, so high throughput system in which you can load 5 samples at the same time. And what we usually recommend for this type of experiment is, in general, having an average of similar type of mass. So if I'm loading 50 milligrams of sample, I would say I would prefer to have sample in the plus or minus 10 milligram in between the 5 experiments. That will guarantee that first, more or less the sample have the same amount of exposure and the same amount of dynamic, so time of experiment. And the second is the difference between the mass uptake, even though we plot it as a percentage mass uptake, the difference between the mass uptake will be more significantly related just to the difference in the material rather than the difference on the initial mass. Now, would it matter if I load 100 milligram sample and another one I load 150? Particularly not. But if I load 150 milligram of sample for one experiment and then I load 5 milligram for the other experiment, then it could become significant. So we try to stay in the general ballpark. If the material is solid, then, as I said, cut it to the same dimension will be the best suggestion we can give. If the material is powder, then that it doesn't really matter, because the powder usually allows for more accessibility for the molecular water. So in that case, it's mainly related to mass. Similar type of mass would be recommended.
Thank you. And a final two-part question from Adrian Gordalas, and he asks, can we use water inside the diffusion cell? And how does the balance work with the diffusion cell mass from only one side? And then the second part is, and so does the water vapor permeability with the DVS stay in accordance with the ASTM E96-E96M? I'll copy that into the chat for you just in case that is more useful, Damiano.
Okay, so for the diffusion cell, the way we usually run the experiment is to have a different humidity on the outside and measure the humidity on uptake, so going in this direction. Now, can you, in theory, have the membrane load water inside the cell and then measure the mass loss? Yeah, you can. The only thing is that you won't have control over the experimental data itself. What I mean by that is, basically, the only condition that you have is the humidity on the outside. It won't be less than 100%, because on the inside you will get 100%. You will put a couple of drops of water, and automatically, when you seal it with the membrane, it will go to saturation point. So you have 100% on the outside, and then on the inside of the cell. And on the outside, you can basically generate a different level of humidity and see how less the mass is dropping. The mass will drop no matter what, because you cannot actually achieve 100% generation in a flow. You can get to 98%, 99%, but not 100, because that is full saturation. You will have condensation. So what you can do is, by adding extra humidity on the outside, you can slow down the loss of water from the membrane on the inside. That you can do. How do you translate that to specific data on uptake is a little bit more complicated. If you just want to set it up in that way, it's doable, but be aware of the fact that it's only a pure mass loss measurement. It will never uptake. The cell is made of metal, and obviously it weighs more, usually more than the membrane itself. So what we usually do is we counterbalance it with an equivalent amount of metal on the reference side. So usually this cell weighs about 275 milligram, and we load 275 counterweights, 275 milligram of counterweights on the reference side to compensate for the mass. So that's the way we usually compensate back for the presence of the cell. Now, from a point of view of uptake, the surface area of the metal is very, very small. Consequently, we do not need to actually worry specifically how much water will go and uptake on the surface of aluminium, because really it's not that significant, especially because the membrane will absorb or lose mass much more compared to anything that this metal will do anyway. So the only thing that we have to do is counterweight on the reference side of the sample. Now, the last bit of the question, you said a code that I don't really recognize, to be 100% honest. So is in the chat, but I'm not aware of this one. I'm really sorry. So what I can do is, we have your email address. I'm gonna have a look at these standard that you report, and I'm gonna get back to you with an email and answer your question, because I don't know what reference is that. Sorry.
Thank you, Damiano. And we have just one hand raised, so I wanted to give them the opportunity just to unmute their microphone and ask their question. So, Ivan Chodak, if you would like to unmute your microphone, you can ask Damiano your question.
I just wonder whether it will be possible to get the copy of the presentation.
Yes, absolutely. I will send to John a PDF copy of the presentation, and then we can share this with you.
Okay, thank you.
No problem.
Thank you, Ivan. And I think that brings us to the end of our hour. So I see we do have a quick question from Tracy. So Tracy, we will get back to you after the presentation by email, but we wanted to give everyone a chance to get to any scheduled meetings they may have now, so we don't overrun too much. So a massive thank you to you again, Damiano. Are there any last messages you would like to share with the audience?
Thank you very much, everybody, for listening to my presentation. And if you have any further questions, don't hesitate to contact us. Thank you.
Thank you, Damiano. And yes, a fair reminder to our audience that if you do have any questions about any of the presentation today, or about DVS in general, you can email them to science@surfacemeasurementsystems.com. And please don't forget, we have another webinar coming up in just a few weeks on the 2nd of November, and this will be covering surface characterization of cellulose and natural fibers by IGC SEA, and this will be with our IGC specialist, Dr. Annette Condor. So please find out more about this and check back often for news on all future webinars at surfacemeasurementsystems.com/webinars. Another huge thank you to our speaker, Dr. Damiano Cattaneo, and to our audience who have been so active and engaged this session. So thank you to everyone, and wherever you are, I hope you have a wonderful remainder of your day. Thank you.